Hello, my name is Ashley Goodnight, and this is my Week 5 reading review for Physics 2212. In this week's EDX videos, we had two main topics. First, there was a review from Physics 1. Then we learned about magnetic fields for both point charges and currents. In our last physics class, Physics 2211, we learned about the torque, or twisting an object secured to a pivot can experience due to a force applied a distance away. We were able to calculate this force using the equation with the force and radius. We could also solve for the magnitude using sine theta, where theta is the angle between the force and radius. We also previously learned that you can think to apply sine to either the radius to represent the line of action or to the force to think about the moment arm. After solving for the magnitude, it's important to think of the direction. We learned to solve for the direction of the torque using what's called the right-hand rule. The diagrams above show how the right-hand rule will apply in this week's lessons. With electric fields, you use the right-hand rule to remember the direction of magnetic forces. If you use your pointer finger in the direction the positive charge is moving, then your middle finger in the direction of the magnetic field, your thumb points in the direction the magnetic force pushing on the moving charge. When you're dealing with negative charges, like moving electrons, the force points in the opposite direction as your thumb. Our final solved direction can be symbolized with a circle and either an X or dot. The X represents moving into the screen, while a dot represents going out of the screen. It's easier to think of it like an arrow. Another way we can solve for torque's magnitude and direction simultaneously is through cross products. Since I took linear algebra last semester, I like to think of cross products as solving for the determinant of a 3x3 matrix, but you can also memorize the formula if it doesn't make sense. Now that we've reviewed some material, let's move on to magnetic fields. First, it's important to know that charges can only cause a magnetic field if they are in motion. For example, let's take a point charge with charge Q, in red on the diagram. It's moving with velocity v in direction v hat. In the diagram, we also have an observation point, radius r away, in direction r hat. The direction of the magnetic field B is actually equal to the direction of v hat cross r hat times the sine of Q. We can also compose an equation for the magnitude of the magnetic field in units Tesla. Note the constants that are below the equation. We can actually create an equation to solve for the magnitude and direction of the magnetic field. This equation, simplified on the right, is called Biot-Savard's law. In the videos, we looked at a diagram of charges moving through a wire and defined a couple of variables such as N, A, V sub D, and solved for a current. However, we learned there's another current called conventional current, which is denoted with the variable I and units amperes, or amps for short. Biot-Savard law also had a law for current, given at the bottom of the slide. This week's lessons apply directly to my major, electrical engineering. At Georgia Tech, EE majors select fields or threads to specialize in. Two in specific, telecommunications and circuit technology, have required courses that build off what we're learning in this class. Those who follow telecommunications take ECE 4350, electromagnetic and microwave applications, while students studying circuit technology take ECE 4391, electromagnetic compatibility. That wraps up my introduction to Week 5. Thank you for listening.